Okay, let's look at an example to see if we charge an inductor with DC sources, how the inductor is going to get charged, or what's the transient condition um, happen if we have an inductor in the system and we suddenly uh, um rise the voltage in the system. So assume we have a uh, circuit like that. So it's going to be, we have a key, and then we have the resistance here, and then we have an inductance here. Uh, so assume the source voltage is 100 volt. The resistance is 50 ohm, and the inductance is 0.1 henries. So assume this is what we have for the t less than 0, and then we will go ahead at t equal to 0, we close that key. So at t equal to 0, we close the key. So as soon as we close the t, it is that that inductor starts to charge. So it starts to store the energy as in form of the magnetic field, and um, the so its voltage, what for example, its voltage is going to be the VT. So it starts at the beginning is 0. We know that when the key is open, there's nothing in there, is 0, and eventually this at the when it's not connected, and as soon as we connect it, then there's going to be the voltage in that inductor, and we know that if we leave it, if we leave the key closed for a very long time, the voltage in that inductance is going to drop eventually to 0, and then it's going to be behave as a single wire. So we want to see how it's that happen here. In this case, and as soon as again when we close that, we are going to have the current goes through this, um, there's going to be the current goes through that, and it's going to be also that current is going to be um, uh, as I said, function of time. We know that at the very beginning when we close the t, when we close the key, the inductance is going to fight the current because it doesn't like changes, so it's going to fight the current. But eventually, after we leave it to stay there for a very long time, it behaves like a single wire and doesn't fight the T, doesn't fight the current anymore. So it gets to some steady state condition, uh, in which cases that we have it behave like as we have only a single source and single resistors. It behave like it's not there. It just can replace it with single wire. So we want to see what's happening between the time we close it to the time that it becomes a steady state. In that transient time, what would happen? So if you remember I was talking, so the very first step that we are going to do is that we need to write the KVL or KCL, depend on what we need to do. So in this case, assume I'm going to write the KVL. Uh, it means that the sigma V in a closed circuit should be 0. So if I go ahead and start, for example, to start to rotate from this point all the way, go back to this point, and write all the voltage I have. So first I get is that Vs, which is negative, is going to be negative 100. So that's a Vs. Then I have the VR, which is going to be the VR. Then I count here that it's going to be the VL, and I know it's going to be 0. So that's what I have. Now, if I go ahead and replace these two terms with the equivalent, so in the resistance, I know that for the resistance, the VR is just I. It's Ohm law, so it's IR, and we know the I here is time dependent, so it's IR for the resistance, and for the inductance we had before, the voltage in the is going to be L di dt. It's what we had previously. So if I go ahead and replace these two in this equation, what I'm gonna have, I take the 100 to the other side, so I'll keep this one here. So I have the IT times R plus L DIT or dt is equal to 100. So this is my differential equation that I have. Now that I have this differential equation, I get first I write the KVL, and then I get my KVL into form of a standard differential equation. And so this is very simple differential equation that we have. We know the solution. If it's gonna, I call this one. I know the solution for this equation is gonna be IT is gonna be K1 plus K2 K2 K1 K2 e to the power of st. So this is the solution. I know this is the solution, so it's the second one. The next step, so this is my differential equation, and this is the solution. The next one is that put the solution in the differential equation. So I put K1 plus K2 e to the power of st in differential equation. So if I do that, so if I replace every place I have IT here, I replace it with K1 plus K2 e to the power of st. So it's going to be K1 plus K2 e to the power of st times R plus L d over dt t of that K1 plus K2 e to the power of st, and this is going to be equal to 100. If I go ahead and rearrange and do this differentiate here and rearrange it, eventually what I'm going to get is I'm going to get R times K1 plus R plus SL K2 e to the power of st is equal to 100. Now, if I simplify that, this is what I'm going to get. And if you look at here, I have three. So this term is constant here. So this is the constant. And this term is time dependent. And again, this term is going to be constant. So here, if I want to satisfy this equation, this time-dependent term should be 0, because if it's not 0, there's no way that you can satisfy this equation. If you have one term that is just keep changing and changing and changing over time, and these two values are constant, it's never going to be satisfied. The only way that this is going to be satisfied is that the time-dependent term should be 0. So the first, the time-dependent term should be 0. This part is not going to be 0. The only way that your time-dependent terms become 0 is that this coefficient becomes 0. So R plus SL should become 0, and therefore the S is going to be negative R over L. And so this is the magnitude of S, and then we can substitute the R as 50 and L as 0.1 here to get the magnitude of the S, but I'd leave it like that here. And then also, if this equation should be set, the constant should be equal to constant. So whatever constant I have on the left side should be equal to the whatever constant I have on the right side, in order that this equation is going to be satisfied. So R times K1 should become 100. And therefore the K1 is going to be 100 divided by R. So if I replace the R as a 50, so it's going to become 100 divided by 50, it's going to become 2. And so we have the value of that as that. So this is how we find the S, and as I said, we can replace also the R is going to be 50 and the L is going to be 0.1. So we have the S and we have the K. So we have the S and we have the K1, so we want to find the K2. When we want to find the K2, the next step is that go to the initial condition and this equation, put the initial condition in the solution. We know that at the initial condition, when the time is 0, when we just close the key, there's no current there. It just starts to have the current. But at the time, right when we close it, the I is 0. So we know that at t is 0, I is 0. And so we put it in the solution. So if I go to the next slide. So we know at t is equal to 0, we know that the I t is 0 right at the beginning. So we put initial condition in solution. It's going to tell us the I initial condition t0 is going to be K1 plus K2 e to the power of S, and t is 0. So therefore, if I use that, I know at the t0 I is 0. So I know that, so it's going to be 0 is equal to the magnitude of the K1 plus K2, and e to the power of 0 is going to be 1. So eventually, so I can write it here. So it's going to be 0 plus, sorry, it's going to be 0. So I at t0 is 0 is K1 plus K2. But that is also going to be the e to the power of 0 is going to be 1. And if we solve that, if we do solve that, so what we are going to get that is the K2 is negative K1, and K1 was 100 was 100 divided by r, so it's going to be negative 100 divided by r. That what we had it before, or if we put the r, is going to be 50, so it's going to be negative 100 divided by 50, and it's become negative 2. So this is going to be the K2. So now we have also the K2. So if I write the solution again, the I t was K1 plus K2 e to the power of st. And if I go ahead and substitute everything, so it, so go back, the K1, if you look at the K1 is the 100 divided by r, or basically that 100 is the Vs divided by r. So I can go ahead and put that, like, put the Vs divided by r, and then plus the K2. Again, that K2 here is 100 divided on that 100 is the Vs, so it's going to be negative Vs divided by r, and then we have the e to the power of that s, and s was negative r over l, or we can write it negative r over l times t. And usually we write the equation again, says so by go ahead and like that. So I can, if I write that equation as this, it's going to be Vs over r minus Vs over r e to the, if I put the t on the top and bring this down and keep the negative sign, so it's going to be the L over r. Or let's put it this way. Usually we write it like that, and the tau is gonna be L over R. So this is the general solution that we have for these particular problems. And also, so we can put the L and R and Vs value in that if we want to have it in form of whatever we have it. So for this specific problem, the IT is become the, as I said, the Vs is going to be 100, the R is going to be 50, negative 100 divided by 50, and e to the power of negative t divided by L over R, which L was 0.1, divided by R, which was 50. So it's going to be this specific, so this is going to be this specific problem. So this is going to be the current, and if we want the voltage, there are two ways of calculating the voltage. Is that if we want to see how the voltage change in the VL in the inductance, the one way of is that if I go back and look at here, this is just using this equation here, the KVL. So let me just write this here, that you know this is the that 100 is Vs. So if I rearrange this equation here, the VL is going to be VR minus Vs. The L is going to be, so if I go ahead, if I rearrange that equation, eventually I know that the the VL is become the VS, whatever voltage I have in the source, minus whatever voltage I'm gonna lose to the R. So in other words, whatever voltage the VS provided is become equal to um, adding these 2 volts. So whatever voltage this was the source provided is separated between the voltage in the R and the voltage in the L. So in other words, the VS, if I arrange this equation, the VS is equal to VR plus VL if I take it the other side. So this is what I'm going to get here, the VL. So I can go ahead and say that the VL over time is going to be VS, which I know is going to be the 100 minus the VR, and the VR I know is going to be IR, or basically IT times R, which the R is 50. So I can go ahead and say it's 100 minus, and then I have the IT here from this equation here. It's got 100 over 50 minus 100 over 50 e to the power of negative t divided by 0.1 divided by 50 times R, which is 50. And it's going to be, when you do that, it's going to be simplified because those 50 is going to cancel out and eventually. So this is the VL over time. This is one way that we can find it. The other way, I just write it here. I'm not going to say how to, I'm not going to do it, but the other way is that we know that the VL is is going to be L di over dt, or so simply we can go ahead and say that VLT. So this is another way of doing the same thing. Is the L, which is going to be 0.1 times d over dt of that here. So 100 over 50 minus 100 over 50 e to the power of negative t divided by negative t divided by 0.1 divided by 50. So either of these two methods is going to give the eventually the same answer. So it's going to, if I write it correctly, eventually it's going to become 100 e to the negative t divided by the tau, which is going to be 0.1. Let me write it. 0.1 divided by 50. Okay. The same here, you will get the same answer here. If you do that, it's going to be negative t divided 0.1 divided by 50. So this is going to be how we calculate the VT. So if I draw them very quickly to see how the current and voltage is going to be changed in this one. So it's going to be T. It's going to be the IT. Going to be the I. And then I have the voltage. So for the current is that when we close the key at the beginning, we don't have any current in the system. Eventually, gradually in the transient condition, we are going to increase the current, and then we get to the steady state condition eventually. That steady state condition is going to be 2. So that's what we have eventually. What we have. So there's no current at the beginning. and the current increase and become a steady state condition. As I said, if we get to the steady state condition, that inductor just behave like a single wire. It doesn't do anything except that store some energy. So this is what we are going to get. In the voltage, let's say the voltage in the inductor, we know that at the beginning it has a very high voltage because the current is zero. There's not going to be any voltage in the resistance, and all the voltage is going to be in the inductor. And eventually the voltage in the inductor drop to zero, and the voltage in the resistance become equal to the voltage of the source. So it starts at the voltage in the inductor is at the very beginning that we close the key is going to be the same as the voltage in the source, and then eventually it just drops down all the way to zero. Eventually, this is how it's going to drop down, and eventually the voltage in the inductance becomes zero, and that's how it's going to behave as a single wire. At the beginning, when we right close the Ti is zero, so the V in the resistance is zero. It's at the very beginning, it look like this. Just when we close it, it's like that we just connect the inductor right to the battery because there is no current. It's like the resistance is not there. But as soon as we are going to have the current, then the voltage in the resistance start to increase, and as the voltage increase here, the voltage start to decrease in the inductor. Eventually, the voltage in the resistance become equal to voltage to the source, and the voltage in the inductor becomes zero. Look at this equation. As I said, the voltage, if I write the KVL here, what's going to be the KVL? It's going to be negative Vs, that's what I write it here, this one, is plus VR plus VL is zero. Now, if I rearrange it, how it's going to be? It's going to be Vs is VR plus VL is Vs. This is what we have. So look at here at the very beginning, how much is the VR? Because there is no current, the VR is going to be zero. You agree? So the VL is going to be exactly the same at the Vs. Now, as the time passed on and the I increase and increase, so the VR starts to increase. So when the VR starts to increase, we know this one is constant, the Vs is constant. So the only way is that the VL starts to decrease. Actually, when the I get to its final value, the VR become equal to Vs and the VL becomes zero.